Thank you very much to the organizers for giving me the chance to present this work at this beautiful conference and this beautiful campus. I'm super happy to be here. Am I well audible, both in Zoom and here? OK, fantastic. So during the previous days, we've seen very nice overviews of techniques to do Bayesian parameter estimation and study different physical effects. Today, we're mostly concerned with the search for ultralight bosons. And since I'm not really an expert on parameter estimation or ultralight bosons or anything in particular, what I want to present today is a case study of how you go about analyzing certain type of signals for which you want to do like a very tailored analysis at the user level. So you assume you have parameter estimation tools like Bilby or Lally inference, and then you have some waveform models, phenomenological, numerical models, etc. And then you go about guessing what could be in the data, what the data is representing. So, and I want to focus it on the case of high mass events, because these high mass events are super challenging, because you don't really have much information about what happens in this type of events. And your results may be strongly driven by what you're assuming it could have happened there, meaning your priors. And the driving case I want to use is 190521, which is the paradigmatic case that we have right now of a conclusive signal that is short and there is not much information about it in the data. And I want to end up talking about the possible nature of this signal as being sourced by a couple of boson stars. So this is the typical signal we find in LIGO. We have this chirp structure. And one can usually identify inspiral, merger, and ringdown in this data. This signal is long, and therefore, there is information about what happened before the merger. So one can make some safe assumptions in here. Now, when we go about guessing what this is, the problem we are faced with is essentially this. We have some data. We have some template model or some waveform that in principle is representing a source with certain source parameters data according to some waveform model, which could be a phenomenological model, could be effective one body, could be numerical relativity. And of course, I skipped one thing here. We are assuming that this is a given model, or we want to guess if this corresponds to a given model plus noise that we believe we have under control, meaning we assume that this is Gaussian stationary and that is well represented by our power spectral density. We consider nowadays this assumption to be rather safe. So how do we perform this comparison? Well, what we're looking is at the posterior probability that this template represented by some parameters data actually corresponds to the data according to some model M. Again, this model could be a numerical model, could be a phenomenological model. And there are two pieces of, or two ingredients we use to do parameter estimation, and there is a third one that is very important to do model selection, so to decide between possible models that describes this source. The first one is the likelihood. So the likelihood, the way I view it, is essentially a measure of similarity between your data and your model. So you're just looking at the data, you have your model, and you say how close these two things are by some kind of measurement. In our case, what we look at is the residuals that we leave in the data after we subtract the model we're comparing with, and we impose that if we have the noise under control, then this residual should be consistent with Gaussian noise. And then we have the prior, which is our prior belief in those parameters actually existing in nature. So the way sometimes I explain what this prior is to undergrads, that is the first time I see it, is I send you to the zoo, and you have some cards of different possible animals. You see something with a horn. It's quite blurry, and you say, well, this could be a rhino, this could be a unicorn, but your prior comes and says, well, unicorns do not exist, so this is a rhino. And then we have this normalizing factor here that we call the evidence. And it's not just a normalizing factor. This is actually what we use to decide which model represents the data best. So this evidence is just the sort of the average weighted by the priors of the likelihood over the whole parameter space. And it's quite useful to understand intuitively what's going to make this evidence to go up or down. So it's obviously going to go up if your model at some points of the parameter space can represent the data very faithfully, so if you have a good fit. Now, it's going to go down if, in order to achieve that huge fit, you need to add a lot of parameters. And in particular, it will go down if some of those combinations of parameters lead to very bad fits or to very low likelihood. So that's going to make your average value of this prior times likelihood decrease, and therefore the model will go down. This is what we know as the Occam's razor. And of course, your choice of priors. So if your priors are so that they are weighing or down-weighing regions of the parameter space where the fit is actually good, then your model is going to go down. And if your priors actually point towards, actually favor regions of the parameter space where your fit is good, your evidence is going to go up. I will get back to this in a few slides. And then when we have two models, we compute this evidence for two models, and then we just compute the probability ratio of the two. Normally, or very often weighted here by some prior odds on our belief of each of these two models being true or existing in nature. So the first challenge we face when we analyze a really short signal is what model do we choose? And not only regarding the nature of the source, but what actual calculation we're doing to go from the system to the actual waveform. So these models can be computed in very different ways. We have AOV models, we have phenomenological models, we have NR surrogates, which are interpolations across numerical relativity simulations. We can also directly use numerical relativity. These models are calibrated or have been fitted to different regions of the parameter space. So two models that in principle represent precessing waveforms or precessing systems can be fitted or actually can be known to work very well at different parts of the parameter space, and then in the rest of the space you just have an interpolation that you tend to believe. And this can include different levels of refinement. So for instance, they can have or not higher harmonics, they may include or not gravitational wave memory, and they may be or not calibrated to numerical relativity, for instance, after merger. These models can also exist for different types of sources. So for instance, the vanilla ones that we always use initially within the LIGO and Virgo collaborations are these models for quasi-circular binaries, because these have been developed for many years, and we have a good coverage of the parameter space. Now we're starting to have more and more models that include eccentricity, and we have even models for dynamical captures. And of course, you can have even different types of CBCs, or of compact binaries. So you can have objects of different nature. For instance, boson star mergers, or you can even have binary black holes immersed in scalar fields. So the question here is, what did you choose initially for your analysis? So for a typical signal, I don't know what this white band is here anyway. For a typical signal, we can see normally a quite long inspiral. And this kind of allows us eventually to say, well, this may be safely assumed to be a quasi-circular binary. And because the most likely object we consider are black holes, we go about analyzing these things with quasi-circular models for black holes. And in fact, there have been searches for instance, eccentricity in LIGO data, and the bounds on that eccentricity are quite strong for most of the events. So this corresponds to the first gravitational wave catalog, and you can see that the bounds on the eccentricity are quite strong. So this goes from 0 to 1, and the largest bound is at 0.05. So this makes us know that the assumption that this may be quasi-circular binaries with zero eccentricity is rather safe. But then we get an event like this, for which you see, in principle, a merger, a ring down, and not much more. And then there's going to be, in principle, a huge degeneracy in the kind of sources that can end up in this signal, or that can represent this signal. Basically, any type of source that can give you the right black hole with the right ring down and something else is going to fit this data. And before going to how you may interpret 190521, I want to make some points about why one would be interested in studying this such a challenging event. So first of all, the pros of studying this high mass event is that you find strong gravity at its full glory. So for this type of events, the merger ring down is in the sweet spot of the detector band. And therefore, if you want to see strong gravity effects, you want to see this. Most of these events, or some of these events, may display higher gravitational wave harmonics, because this gets triggered during the merger and ringdown, mostly. And then you have access to very fancy waveform morphologies that are quite differing from the typical exponential ringdown, exponentially decaying ringdown. Because there are higher harmonics and you have strong gravity at its best, you may do a quite strong test of general relativity. In particular, for instance, you can try to test the no-hair theorem, as quite a lot of people have tried in the past. You may also observe strong field phenomena in this merger ringdown, as for instance, gravitational kicks. The merger and ringdown is when the gravitational kick actually builds up. And lots of times, these mergers will involve very highly massive merging objects that may populate the pair instability supernova gap. So this can give you, this can either give you clues about where this gap actually is, or can give you quite a lot of information about in which environment these black holes are living. And these are the cons. So con number one, these things are very difficult to detect. The signals are really short, and therefore glitches present in the detector can very easily mimic them. So it's very difficult then to tell apart signals from actual noise. Because they may show strong higher harmonics, and our templated searches do not yet include them, we may be missing quite a lot of them because our templates are just not faithful representations of these signals. And as I said, interpreting them is also really tough because there is little information about what happened before the merger. Many times, the waveform models are going to be actually hitting the limits of their calibration regions. So there is this fundamental uncertainty of, am I sure that my waveform model is actually correct or not in here? And precisely because there is not much information here, the results can be strongly influenced by your prior choices. So anyway, now you go about analyzing this event under the vanilla assumption of a quasi-circular binary. This is what the LIGO and Virgo collaborations did. And then you find out that the remnant is an intermediate mass black hole. So the posterior distribution for the final mass is well above 100 solar masses. You have a primary black hole that is perfectly populating the pair instability supernova gap. And you find a mild signature of precession in such a short inspiral. If you're wondering what this comes from, it comes from the fact that this is ramping up really fast. If you try to fit this with aligned spin signals, you will see that if you look at it backwards, the decay of the amplitude of the signal is much lower. So only the modulation that precession causes in the signal can cause that within the quasi-circular paradigm. Of course, you can also measure precession via the parameter chi-p, which is what we do. There is a very nice study of how different models and different assumptions about what happened in this merger happened by Hector Estellés et al. It was from June, so I really recommend to read that. But it happens that precession can actually be mimicked by eccentricity. So now you start to play with this type of degeneracy. So the way you can see this is, you can see here a waveform in the Fourier domain from a head-on collision. Actually, this is a super extreme eccentricity. You try to fit this with precessing signals or precessing templates. You see you can, but you can really not do it with aligned spin systems. So if you had something like this in the data and you just do the analysis that I showed before, you would just think that this is genuinely precessing, whereas it's actually eccentric. And in fact, there have been several studies or searches for eccentricity in the system. So Isabel Romero-Shaw in Monash showed that, well, if you use a model that only reaches a minor or a low level of eccentricity, then your posterior for this eccentricity saturates. So you just need more. There is, oops, there should be a plot here. There is this study by the Rochester and Florida groups in which they compared the signal to numerical simulations with high eccentricity, high precession, and they achieve a very good fit. With Tony, Alejandro, and other people, we went a bit, before, yes. There is this study also by Rosella Gamba where they, and colleagues, where they show this is also consistent with a dynamical capture. So you're seeing a whole slew of possibilities in here. Going up in levels of eccentricity, as I said, with Tony and Alejandro and other people, we studied the possibility that, well, maybe this is head-on because the signal is really short. You find out this is not possible because the head-on signal is too short to fit the data. And it's because it lacks any pre-merger signal. When you have a head-on collision, the two black holes collide, you get the remnant, it rings down, and that's it. And also, the final spin you get is actually too low to reproduce the spin, the final spin predicted by binary black holes. And you may say, well, I can just spin up the black holes and then get a higher final spin, but this is not possible because the black holes are bounded by the cosmic censorship that imposes a limit of spin equal or lower than 1. So this gets us to the boson-star mergers. So why boson-star mergers? This is not the reason why we looked at boson-star mergers. I will tell it later. But boson-star mergers are essentially self-gravitating Bose-Einstein condensate made of ultralight boson fields. They can mimic most of the properties of black holes, but they don't have an even horizon. They don't have a singularity. And because of this, they can have spins larger than 1. So there is no problem with cosmic censorship. And because of that, they can give us the final black hole we were after. So this is actually the reason we explored this option. And of course, they can give us a highly spinning remnant black hole. They have all of these. So a boson star merger is going to have the same properties as a black hole merger, inclination, masses, spins, etc. But there will be two particular physics parameters that are new for boson stars. One is the oscillation field, so oscillation frequency of the bosonic field. And this determines the compactness of the star, so how similar to a black hole it is. And a boson mass, which once you have the frequency, the oscillation frequency determines the maximum mass that this star can have before imploding into a black hole. And as Simina said before, there are very, very nice candidates for forming dark matter because of their properties. They basically don't interact with anything. So there is a whole slew of ultralight bosons you can consider: scalar, vector, tensor, and real and complex. And searches for effects of this boson so far have focused on scalar bosons. And this is because the scalar bosons can form either these clouds around black holes that can extract angular momentum on the one hand and also lead to a continuous emission of gravitational waves. So there have been searches for both of them that have placed limits on the possible masses of these bosons. But when it comes to forming stars, it turns out that if you want to have a stable spinning star, you need to attach to the spin case. Sorry, to the spin equals 1 case, so to the vector boson case. And this forms what we know as a Proca star. So from here on, I will be talking equivalently about boson stars and Proca stars. A black hole merger looks like this. You have an inspiral merger ring down and a final black hole. This is not new to anyone. But in the case of a boson star merger, you have an extra phase in which you form a hypermassive boson star. As I said before, depending on the compactness of the star, this may collapse to a black hole or not. And if you attach to those that collapse, the less compact this is, or in other words, the higher spin it has, it will live for longer. So it will emit these types of pulses before it implodes and collides and rings down. In our case, of course, since we want to reproduce 190521, we will be attaching to this case in which the final star is quite compact and it implodes almost automatically, or collapses almost automatically. So you can simulate these mergers with numerical relativity. Nico Sanchez in Aveiro did it using the Einstein toolkit. And well, this is the properties of the initial set we use. So we're attaching to an equal mass mergers in which we just vary the oscillation frequencies of the two fields, or what's the same, we're varying the spins. This is the initial separation. We place them quite far away to prevent the junk radiation to be close to the true emission. And these are the modes we include. Very importantly, whereas the emission from circular binaries is fully dominated in most cases by the quadrupole mode, here these two are codominant. So if you are at inclinations that are not face-on, you may see a really strong 2-0 mode. And this is just a GIF with, GIF actually works. That shows how the waveform varies as we vary the oscillation frequencies of the two fields. That's just for pictorial purposes. So, well, again, this is the basics on model selection and parameter estimation. And for the experts in the room, this is just the settings we use for this particular run. So this is the frequency range we explore. There is basically nothing below 11 hertz in that LIGO can see. We use Bilby, so we implemented this numerical relativity parameter estimation stuff in Bilby. And we're using the sampler CP-nest. In a posterior analysis, we actually use Dynasty. And then our priors cannot be the typical priors that everyone uses, for instance, uniforming the two masses, because we have a discrete set of simulations. So what we use is a uniform prior in total mass, because these simulations can be trivially scaled to any mass. And in order to compare to black hole merger models, we choose the same prior for those models combined with a uniform prior in mass ratio, just to make a sort of apples-to-apples comparison. The rest of the priors are standard, and in particular, we'll come here later, but we start with a uniform prior in comoving volume, and then we try other stuff because of reasons I will say. So this is the simulations we used initially. So we compared the signal to a uniform grid in the oscillation frequency of the two stars. So we can say that this is actually our prior. So we do parameter estimation, basically comparing the data to each one of these simulations, for which we vary continuously the orientations and total mass parameters. And the question is, how do you go from that to continuous posterior distributions for the whole set? So as I said, for each of these simulations, so if you think about black holes for each combination of spins and mass ratio, we get continuous distributions on mass, orientation, azimuth, inclination, sky location, et cetera, et cetera. And then you need to combine this to get a joint distribution. So there are a couple of ways of doing that I can think of. The first one is what the Rift algorithm does. This was developed by Jacob Lange et al. In RIT. And what they do is essentially they try to interpolate those continuous posteriors across all of your parameter space, which requires, it's quite non-trivial. In our case, we say, OK, we're just going to draw samples from each simulation proportionally to the probability that that simulation is the right one. So in other words, proportionally to the marginalized evidence we get for each of these simulations. This is equivalent to saying, OK, this is actually our prior in these two parameters. So well, in this case, it's the same frequency for both stars. So we are basically using a uniform prior in the frequency of the two colliding stars. And let me dive into the results. So first of all, the total redshifted mass we get is a bit smaller than you get for binary black holes. So this is the result from LIGO and Virgo. This is what we get. And this second column, don't pay attention to it. This is like an exploratory run with it. And this mass is smaller because head-on collisions are weaker than circular mergers. So you need to emit less gravitational waves to achieve the final black hole mass. Because the emission is much, much weaker, you're going to infer a distance that is much smaller. So it's a factor of 10 smaller. This distance is comparable to 15914, for instance. And because of that, your redshift is going to be much smaller, which means your real source frame mass is going to be much higher. So this is 80 solar masses higher than the result from the LIGO and Virgo. Anyway, the conclusion that the final object is an intermediate mass black hole is of course safe. You can estimate whatever parameters you want, but then you need to actually say whether your model is preferred to the vanilla circular black hole one. So when I do so, I, of course, look at the log evidence or the log base factor for each of the models I have at hand. But it's also useful to look at the maximum likelihood you get, because this log base factor is basically bounded by this value. And if you do so, you can understand whether a large or small base factor comes from a poor fit of your model or just from prior effects, such as your parameter space being too large. And I will talk about this in a second. So anyway, if we just look at this kind of vanilla analysis, what you see is that the base factors we get for the Procaster mergers are slightly larger than the one you get for the black hole family. So you would say, for each of these two families, I prefer them, with respect to the vanilla case, 3-to-1 and 7-to-1 odds. Now, this standard analysis, as I said, assumes the very reasonable assumption that your sources distribute uniformly in volume or in comoving volume. But that's very reasonable, but that's going to have an effect. And that is going to have the effect that it's going to prefer by default loud stuff that you can place far away, and therefore is more likely to exist. So we wanted to gauge this away, not because this is not reasonable, but to say what would happen if our mergers were louder, intrinsically louder. In other words, if we had circular mergers. And you can do so, or pretend you do so, by saying, OK, I'm going to choose a prior uniform in luminosity distance so that this intrinsic luminosity bias, or this bias towards loud stuff, gets away. And this is what you find. And your evidences in favor of these two models actually increase very sensibly. And this makes sense because if you remember, the distance we get for these two models here is 10 times smaller than the one you get for this one. So these are being strongly killed by your distance priors. This is not to say that this is the numbers we believe, but is to say, well, if we had circular mergers, maybe this would happen. But you can also say, well, am I overkilling the black hole model? The black hole model has precession. So it has, each black hole has 80 intrinsic parameters, whereas our Procastar models have 3, meaning the total mass, the frequency of the first star, the frequency of the second. So you're exploring a very vast parameter space to achieve a given fit. And maybe you don't need to explore that much of the parameter space in order to find that fit. So maybe you can restrict to given slices of the space of black holes and push up your evidence. So the first experiment you can do is to remove precession. Let's see if a line spin can explain this signal. And you find that it cannot. Your base factor decreases a lot. Your log likelihood decreases a lot. So precession is a necessary complication of the model. You can say, well, if I look at the posterior for the mass ratio, I see that high mass ratios are actually discarded by the Ligon-Virgo analysis. So let's restrict to lower than 2. Let's not explore those apparently useless portions of the parameter space. And then your evidence goes up. So nice. What happens if I restrict to mass ratio 1, which is actually the most preferred value for the Ligon-Virgo posteriors? And it's actually the mass ratio we're using for our model. And you rise this base factor quite a lot, but you still cannot beat one of our Procastar models. So best case scenario, the two models, black holes and Procastars, are equally preferred. And well, once you have a parameter estimation done with these Procastars, you can wonder, do I find any new physics here under this scenario? Can I measure any new parameter? And the answer is you can. So this is the posterior distribution for the frequency of the two stars. This value on its own is pretty meaningless unless you know exactly how this relates to compactness. But once you mix this with the total mass, you can find the mass of the ultralight boson that would be forming up these stars. And there are two aspects here. You get this value, around 8.7 times to the minus 13 electron volts, which is, I believe, consistent with current bounds. And actually, those bounds are for scalar bosons. And we are talking here about vector bosons. So it's just a numerical match. And you completely discard 0. So if you ever believe this is a head-on collision of Procastars, then there is this new particle in there. Again, also I need to say the head-on scenario is super restrictive. So it's making these posteriors being super shrink with respect to what you would get if you had a complete model that allows for circular binaries and more levels of eccentricity. You can also ask how massive can one of these Procastars be before collapsing into a black hole. And you're interesting in this question because if you want to reproduce LIGO-Virgo data, you want this star to collapse and produce a ringdown. Otherwise, you will never match one of those observations. And you can compute that mass, and you obtain a value of around 175 solar masses. So this is the mass you need before you implode into a black hole. So this automatically discards previous LIGO-Virgo events to this one as head-on collisions of Procastars with these field frequencies. Now, we extended this study now to almost 800 simulations. So this is our new grid in simulations. And we've performed this comparison with more black hole models. So the philosophy here is let's try every black hole model, every possible prior, and let's see what the largest evidence we get is. If our Procastar model still beats all of this, then we cannot be blamed that we didn't try to favor the black hole model as much as we could. And the results are essentially unaltered. So we get parameters that are fully consistent with the initial study. We get a very similar boson mass, so that's nice. Results are robust. And we get then still a mild evidence in favor of the Procastar model. So this is nice. Now, what about more events that we may analyze under this scenario? So there have been more detections of black holes since we did, of course, this or gravitational waves that are short after we produced this study. There are a few events in the GWT3 catalog that are interesting. There is another one in the GWTC 2.1, but I was particularly interested in this one. This event is S200-114, so it's not yet cataloged as a gravitational wave. And this was the loudest trigger that appeared in the search for intermediate mass black hole mergers of the LIGO and Virgo collaborations. It has a quite large significance, or not negligible, but it was not labeled genuinely as a detection because this does not cross the threshold to a genuine detection and was only seen by unmodeled searches. So searches that use templates could not find this event. And also, funny enough, if you try to do parameter estimation on this with the 3 vanilla models we use, namely phenomenological, EOV, and NR surrogate, there is no way the 3 agree. So I put the blame on the models. So some people were arguing that this means that this is not a binary black hole. What this means is that the models are not predicting the same thing for the same parameters, so the same waveform. So you can do the same study with it using our Procastar model. So you predict some parameters. Some highlights is that the final spin is very common among LIGO detections. Of course, we only find we find a reasonably equal mass ratio because that's the limits of our model. It's super nearby, 100 megaparsecs, which means that our distance prior is going to kill this model quite strongly with respect to binary black holes. And we obtain a boson mass that is not fully inconsistent with 190521. And again, these posteriors are super over-restricted because of the restriction to a head-on collision. If you're wondering why, that's because at the end of the day, what you're trying to do here is to fit the final spin. In order to fit the final spin, you want to have a given combination of your individual spins and the orbital angular momentum. We are lacking the orbital angular momentum in here. So if we started to do less eccentric configurations, we would have that contribution to the angular momentum to the final spin that would allow us to reduce the spin of the 2 stars and therefore vary the oscillation frequency of the field and therefore enlarge all of these posteriors. And there is, again, a slight preference for the Procastar scenario when we as compared to when we compare to black holes. And there's also room for improvement. So this is how the log-based factor or the marginalized evidence for each of our simulations looks. And you can see that the darkest points are pointing towards the limits of our model. So I guess that if we start to play simulations over here, these evidences may go up. OK, I think this is actually my last slide. So once you sort of believe you have 2 detections and you have done this model comparison with black holes and Procastars, you can start to ask the question of, so which of the following scenarios is more likely? 2 black holes, 2 Procastars with different bosons, 2 Procastar mergers with the same boson, or 1 and 1. So if you attach, let's say, to the vanilla or preferred model that we usually use for these high mass mergers, which is the NR surrogate, this is the probabilities you get. So the probability that 2 are black holes is pretty small. It's in the 0.07 level. And because the 2 masses are not very consistent, the probability that you have 2 boson-star mergers described by the same boson is also quite small. The probability to have 2 black holes gets larger when you go and choose as a black hole model the model that gives you the right fit, the best fit to the data, namely, in this case, phenomenological models. And this is at the 20%. So anyway, just bold-faced looking at these results, it seems that if you believe both are gravitational waves, it's not very likely that both are described by black hole mergers. Of course, on top of this, you need to put a prior on your belief that two boson stars can exist and collide in a head-on collision, which is another completely different story. So I think I'm going to end up here. So I think there will be a lot of time for questions if there are any. So events like 190521 are bringing us in the realm of we didn't really know what we're observing. So we'd better try as many models and as many priors as we can just to figure out what could be in there. Again, the origin isn't clear for this type of signals. And when I mean the origin of the final object that you are witnessing, because you have little information of what happened before. And therefore, priors may strongly influence your result. We found that this thing is consistent with a Proctor merger. We were that lucky, or I don't know. And this is approximately the mass we get. And this is, I want to mention that our waveform model is very limited. So, of course, a head-on collision is completely impossible astrophysically. But the philosophy here is that you are almost using a toy model that is super fast to calculate. It has only been developed for a year or year and a half now. And this already fits this data better than binary black hole models. So this is promising, and it's a good motivation to explore a huge room for improvement that there is. In particular, to perform simulations for less eccentric configurations that are not only more realistic, but will also be intrinsically louder. So you can place those further away, and then your analysis will like them more. And when you have less eccentric configurations, you will also have a more highly spinning transient hypermassive star. And as I said, this hypermassive star will emit these characteristic pulses. And if you see those, then you can conclude more confidently that you may be witnessing a protostar. Of course, if you want to find those, you either need to rely on unmodeled searches, which are not optimal once you know the template for the signal. So we may want to explore a templated or targeted searches for this type of boson star mergers, for which you can see the characteristic emission. And of course, once if you're optimistic and you believe at some point you will have many events that are consistent with boson star mergers, then you can start to check or to ask the question of how many ultralight bosons are there, if any. So I will end here, and if there are any questions, I'll be happy to take them.